So far, we've done the first 2 lectures on our monad journey, and in particular, we've worked up to the definition of what a monad actually is in Haskell. We essentially rediscovered that by looking at a simple example. And then we saw 3 concrete examples of monads in Haskell. We saw the maybe monad, we saw the list monad, and we saw the state monad. So what we're going to do today is we're going to start off with a bit of a review as normal. We're going to review the definition of a monad. We're going to review how the state monad works. And then what we're going to spend most of our time doing today is working through an example of using the state monad in practice. And this is going to be to do with relabeling trees. So let's first of all have a quick refresher about the Haskell class declaration for monads, and everything is just contained on this one slide here. It's a simple 4-line declaration. So what the declaration says, if we look at the header first of all, it says if you want to be a monad, first of all you need to be an applicative functor. And then you can be a monad then, provided that you have 2 functions of the appropriate type. So the first function is our old friend, the bind operator. Well, I hope it's an old friend by now. It certainly should be by the end of the course. And what bind does is it gives you a generic way of sequencing things together. So what we're going to do is take an M that returns an A, and then we're going to take a function that processes that A and gives you back an M that returns a B, and then finally we're going to get back an M that returns a B. And again, this was just a simple generalization of the bind operator which we had for the maybe type. So for maybe, we took a maybe of A, and then an A to maybe B, and we gave back a maybe of B, and this gave us a simple way of sequencing computations that can fail. And what the bind operator in general does is just gives us a way of sequencing things for an arbitrary monad, not just the maybe monad. And then in order to be a monad, we learned last day, you also have to have another little function as well called return. And return simply goes from A to M of A. And return also has the same type as pure, and actually it's defaulted to the pure function from the applicative class. But it's there for historical reasons, also for connections with category theory that we discussed last day. When I'm defining a monad in this course, I will often manually define the return function rather than using this simple default definition, because I want to make sure that we all understand what's going on. So let's move then to the definition for the state monad. So here was 3 of the components which we started off with last time. And the idea in the state monad is that you're programming with some kind of state, and state is just something whose value changes over time. It could be a counter, for example, and as time goes on, you're incrementing that counter. But at this point, we don't actually care what kind of state we're manipulating, so we're going to leave this abstract and just write nothing in there at the moment. But when we come to consider an example, such as the tree relabeling example, then we'll have to actually instantiate what the particular state type is. But for now, we'll just leave it unspecified. Then we learned last time around what a state transformer is. And the basis of a state transformer is it's kind of exactly what its name suggests. It takes an input state, and what it's going to give you back is some kind of result value and then a possibly modified state. So the kind of key part of a state transformer is it transforms an input state into a possibly modified output state, but along the way you can produce a result value as well. And that's why the type is parameterized. You see on the left-hand side, we have a state transformer that returns a result of type A, and that's because we have this little type variable in here, so we need to make it a parameter of the type. Because of the way that Haskell works, we can't just define the st type as a function of that type, which is what we'd like to do. In order to make it into an instance of the monad class, we need to introduce a dummy constructor, which we called s, and we use the new type mechanism rather than the data mechanism, because that ensures if you have a data type with one constructor, then you don't pay any runtime price for messing around with that single constructor. Okay, so that's what a state transformer was. And then finally, we defined a little helper function, which is essentially just going to apply a state transformer for us. So it's an application function. It's going to take a state transformer as its first argument, and then a state as its second argument, and it's simply going to get rid of the dummy constructor, the big S, and apply the state transformer to the state. So this will give you back a result value and a possibly modified state. So again, this is just a little helper function which is going to streamline the definition of some of the functions that we define on state. So before we move on to actually revisiting the definition of the state monad in Haskell, I want to get you to think about a simple question to do with types. And this will actually give us a slightly different and more refined way about thinking about the state monad. So I'm going to write down two function types. The first one is char to int, and the second one is char to st of int. And then we're going to think about what's the similarities between these two types and what's the difference. So let's look at the first one. So over here we have functions from char to int. So what do these do? Well, we can think about these as just being a pure mathematical function, because that's what functions are in Haskell. And we're going to take an input and we're going to give an output. And the input's going to be something like a character C, and the output is going to be something like a character N. So this is the kind of hallmark of a pure functional language such as Haskell. If I have a function from char to int, all it is a box that is going to take a character as an input. It's going to process it in some way in a pure manner. It's not going to interact with the outside world. It has no side effects. And then it's going to deliver me a number n. So very, very simple. We're very familiar with this idea. So let's now think about the kind of functions on the right-hand side. So these also take a character as an input, and they also deliver an integer as an output, but we have this st guy involved as well. So what's actually going on with this? So we know what a state transformer is. A state transformer is a function that takes a state as an input and then gives back a result value, here a value which is an integer, and then a possibly modified state. So if we were to expand out the definition of st here, and for now, I'm just going to forget about the dummy constructor because it's not really important for this explanation. So this is really the same thing as we're taking a character as an input, then we're also taking a state as an input. That's unwinding the st. And then what we're going to get back is an integer as the result value, and then a possibly modified state. So when I write this type here, what I'm really meaning is this here. So we see we also have some internal state which we're manipulating. So it's not just a pure function that's taking a character and giving you an integer. Kind of internally, inside the st construct, we're also manipulating some kind of internal state, which is, as we'll see shortly, some kind of effect. So let's then play the same game now and draw a picture of these kind of things and see what the difference is. So I'm going to draw the picture here. So what we have is functions of type char to st of int. So as before, they're going to take a character as an input and give back a number as an output. But we know under the hood, or inside the st machinery, there's also a state as well. So under the hood, we've got a state coming in and a state coming out. So these two pictures here show you the essential difference between functions of these two types. With the first one, we've just got a single character coming in and a number coming out. Whereas with the second one, we've got the same character coming in, number coming out. But under the hood, we've also got a state being manipulated as well. And what I'd like to do is get you to think about this in terms of things being hidden and things being revealed to you. So let's have a look at the idea here. So the way I'm going to start to think about this is imagine that half of this box on the right hand side is underwater. So here's my bad attempt at drawing some water. So there's a water line. Imagine the whole underside of the box, so the under part of the box is under the water. So now you can start to see a different way of thinking about viewing the st type. So if I think about looking at functions from type char to st of int, so I've got the character coming in here and the integer coming out here, and I see those above the waterline. Okay, these are very clearly visible to me, just like they're very clearly visible in the type. But the st guy here, that's hiding for me, or it's abstracting away from the fact that really behind the scenes, or now let's think about it as being kind of under the water, we also have a state coming in and we have a state coming out. So I think this is a very useful way of thinking about the state monad. There's things that you can see very clearly, like the character coming in and the integer coming out, and then there's things which are still there, but they're hidden from you most of the time. And that's what the state monad machinery is going to handle for you. It'll handle all of this kind of gory stuff under the water to do with the manipulation of state, and you pay attention to the stuff which is above the water level, which is the things coming in and the things coming out. So what we can do now is, with this new kind of more refined way about thinking about the state monad, we can review the definition in Haskell. So we're making an instance declaration. So we write instance, and we're defining a monad, and we're declaring st for state transformers to be a monad. And let's do it with the easy function first. First of all, I'm going to look at the return function. So return, in this case, has type A to st of A. And then here's the definition which we constructed last day very carefully by looking at types. So what we did is we were returning the value x, which is of type A. And then what we need to do is build a state transformer. So we will have the dummy constructor s, and then we'll take an input state small s, and we need to return a value of type A and a state. And as we discovered last day by looking at the types, the natural definition for this on type grounds is simply to return the input value x and return the state unchanged. So we can have a little picture of this, just like we did last day. So we have a box, and I can call the box return. That's what it's called. And we've got two connectors coming in, and we've got two connectors coming out. So what we have on the top is we have the value x coming in, and it's actually just going to go straight through, and it's going to come out the other side. And then down the bottom we have the state coming in, little s, and it's going to go straight through to the other side, and we get the little state coming out. So this is exactly the same picture that we drew last day, but now we can use this water idea to actually kind of understand it in a slightly different way. So when you look at the type of return, you see that it's taking an A as an input and giving an A as an output, and then you have this st stuff in the way here. Okay, so what the st stuff is doing is really hiding the fact that there's a state kind of under the hood, or kind of below the waterline, if you like. So if you just look at the type of return, let me just change back to yellow again. The type of return is you take an A and you give back an A. And that's what you see here. You take an A in, that's an X has of type A, and it's going straight through, and you're getting the same value coming out as well. But what the blue part is telling you is that there's really some state involved as well. So I've colored the state, transformer thing up here in blue to indicate that that's kind of the stuff which is getting hidden for you. And down below we see that we also have a state coming in and we have a state coming out. And again, I think this is a nice kind of pictorial way to think about what's actually happening with this definition. So all that remains now is to complete the definition for the state monad by defining the bind operator. So in this case, bind takes an st of A to an A to an st of B, and then finally it's going to give back an st of B. And this is actually quite a sophisticated type, because remember that each of these st things is actually a function which transforms a state into a result value and a possibly modified state. But what we found last time around is that by kind of tracking through the types very carefully and thinking what have we got and what are we trying to make, we kind of came up with a natural definition for this. So let's quickly review this and then we'll look at the picture. So if we take a state transformer st, and we're feeding its result into a function f, what are we going to do? Well, we're going to be building a state transformer, so I need the dummy constructor s, and then we're taking an input state, which is little s, and then we're thinking, what are we going to do? Well, the basic idea is we're going to be applying this state transformer to this input state, and that's going to give us a result, and we're going to be feeding that into the function f. So how do we actually write that down in Haskell notation? Well, what we did last time is we had a let. So we're going to apply the state transformer, and that's going to give us a result value x and a possibly modified state s prime. And that's the result of applying the state transformer st to the input state S. So we apply one to the other and we get a new result value X, or we get a result value X and a possibly modified state S prime. And then all we're going to do is complete the definition by, we're going to apply the state transformer, which results by feeding the value X into the function F, because notice up here, the function takes a value, which is going to be the value which comes out of this thing. We apply the function to the value and we will get a state transformer. And then we can apply that state transformer to the latest copy of the state, which is S prime. And then we're done. Okay, so this is the appropriate form of sequencing for the state monad. And again, it's a kind of technical little definition, but it's the obvious definition if you just track through the types. So now let's have a look at this in terms of pictures, and in particular in terms of this idea of some things being kind of hidden below the waterline by the ST machinery. So what we have is we have a state transformer called ST, and we're feeding its result into a function F. So what's happening is we're having a state coming in here, S, and it's being transformed into a possibly modified state S prime, and a result value X. And then both of those are going into the function F, and out the other side will come a possibly modified state. So let me just call it S double prime. I mean, it's not named above. The application here will give us a pair comprising a result value of type B and the possibly modified state. Let me call the result value X prime and the modified state S double prime. So that's the picture which we had last day, but what I like to think about now is this idea of some things being hidden and some things not. When you look at the type up here for the bind operator, you see it's a state transformer for that returns an A, then we go to A to STB, and we get back a B. Okay, so all the kind of state machinery is kind of hidden inside ST. Okay, that's hidden inside the monad machinery. So we can think about the waterline here now. Where actually is it? So the waterline is here. The stuff above the waterline is the values flowing through this computation. Okay, and everything below the waterline is being handled for us by the bind operator. So the bind operator is handling the stuff in the blue. It's kind of secretly taking the state. So we see the state here. It's coming in, hidden on the right-hand side, and it's going through, and we get a new state S prime here, and then finally we're going to do an application, and we'll get a new third state S double prime. So that's all kind of hidden for us inside the state machinery, whereas as a programmer, all we're really concerned is these values which are flowing through above the line. So again, if you have any difficulties understanding the state monad, kind of track through these definitions for yourself and think about what's hidden and what's revealed to me, and how can that kind of help you to understand actually what's going on. So what we're going to do for the rest of the class today is we're going to do a simple worked example of actually using the state monad in practice. And the example we're going to look at is a simple exercise to do with relabeling trees. So we'll kick things off by just defining or declaring a simple data type of trees. So we're going to have trees, which is a parameterized type. It's going to contain values of type A, and a tree is either going to be a leaf, which contains a single value of type A, or it's going to be a node which has two trees as parameters. Okay, a left subtree and a right subtree. So the data type of trees that contain values of type A, they either are leaves, which contain a single value of type A, or it's a node with two recursive subtrees. So this is a type of binary trees that contain data in the leaves. So let's have a simple example of a tree. So I'm defining a tree T. It's going to be a tree, let's make it a tree of characters. And let's say we're going to have the characters A, B, C, and we'll make it a left branching tree. So we're going to have a node at the top, and then we're going to have a node to the left, and that's going to have two leaves, one which contains the A, and one which contains the B. So that's a left branch with A and B in it. Make sure I close my brackets correctly, and then we have another branch which has got the character C. So this is a left branching binary tree which contains 3 characters A, B and C. Actually, maybe I'll draw a picture of this because it illustrates a bit more clearly what's going on with that particular tree. So I have a picture here. So let me depict the node by a blob. So there's one node, then I have a node to the left, another blob, and then I have the character A sitting in a leaf. I have another character, this time a B, sitting in a leaf, and then I have the third character C sitting over here. So when I wrote all this stuff to do with leaves and nodes and brackets, I mean, essentially I was just trying to capture this kind of left branching tree. So now we can understand the problem we're trying to solve. So it's to do with relabeling trees. So what we want to do is define a function that relabels each leaf in such a tree by a fresh integer. And by fresh integer, I just mean it's got to be completely unique in the tree. So for example, if I took this tree, so I have the characters A, B and C sitting in the leaves, what I'd like my relabeling function to do is forget about whatever those labels are and replace them by fresh or unique numbers. So for example, I could just replace each of these things by the numbers 1, 2 and 3. So what's the basic idea then? So essentially, we want to define a function which takes a tree of A things and is going to give us back a tree of integers. And the integers will be the unique or fresh labels in the tree. Of course, if we're doing this in a pure functional language such as Haskell, we can't have some kind of global variable, which is the next fresh integer. What we actually need to do is pass that in. So actually, we can't write a function of this type directly. What we'd need to do is write a function with a slightly more complicated type. So what we'd need to do is we take a tree of A's as input. Then we're going to take the next fresh integer, or rather the first fresh integer. So maybe that would start off as being 0 or 1. And then we're going to pass out the labeled tree. So we're going to pass out the tree of integers, and then we're going to pass out the next fresh integer, which somebody else could use. So this kind of function we can write in a pure functional language such as Haskell. So we're essentially taking in an input state here, which is the first fresh label, and we're outputting an output state here, which is the next fresh label, which somebody else could use later on. So of course you can see this has got something to do with the state monad. That's the whole point of the example. But what we'll do first is we'll write this helper function that will let us redefine or let us define a labeling function on trees. We'll write the helper function first without using monads, and we'll thread these integers around manually, and then we'll see what a pain it is, and then we'll see how we can do it in a much more clean and simple way using the state monad. So I'm going to call the helper function rlabel because it's going to relabel a tree. And as we've just seen, it takes a tree of A's and the first fresh integer, and it's going to give back a labeled tree, so a tree of integers, and then it's going to give back the next fresh integer, which someone else could use. So in the usual way, we're going to write this with a skeleton first of all. We'll write what happens if we relabel a leaf. So we get a leaf whose current value is x, and we're going to have the fresh label n, and we'll figure out what to do. And then we're relabeling a node with 2 subtrees, L and R, and the first fresh label is n, and we figure out what to do. So let's look at the base case first of all. If we have a leaf whose current label is x and n is the next fresh label, what are we going to do? Well, this is a very simple case as usual. We're simply going to replace the leaf label by the first fresh integer, which is n. And then we need to remember to increment the integer so that if somebody else is using the next fresh label later on, for example recursively, then we're not reusing the same label n, because we've already labeled that in the leaf here. We want all the labels to be unique or fresh, so we remember to increment. So now we come to the recursive case. How do we relabel a node with a left subtree L and a right subtree R, and n is the next fresh label? Well, I'm going to do this recursively, and I'm going to have a little where clause, which is going to do the recursive stuff for me. So what I'm going to do is, first of all, I'm going to relabel the left-hand tree. So make sure I get my indices right here or my primes right here. I'm going to relabel the left-hand subtree L, and I'm going to pass in the first fresh label N. Okay, so I'm relabeling the left-hand subtree, and that will give me a labeled tree, L prime, and it will give me a new label, N prime. That's the next fresh label. So then I can do the same with the right subtree. I can relabel the right subtree, and I make sure to pass in the most recent or most fresh label, which is N prime, and then that's going to give me a relabeled tree R prime and another fresh label N double prime. And then I can package all of this stuff up. So what I'm going to do then is return a node, and it's got a labeled left subtree L prime, a relabeled right subtree R prime, and then we need to return the latest fresh label so that someone else could use this recursively if they wished, and that's N double prime. So this is a perfectly valid definition for the relabeling function without doing anything fancy with state monad. We're just threading around the next fresh label. But there's a bit of a problem with this. Well, there's two problems really. One is there's quite a lot of plumbing code involved here. If I actually track through how I'm threading the fresh label, it's actually quite complicated. So if I do this in red, I'm taking the first fresh label in here, N, and it's getting passed down into this function here. Okay, so we're threading it into the rlabel function. And then that value is coming through the rlabel function, so it's coming through the rlabel function, and then we're getting a new label here. And then that label is being threaded down into the relabeling function again to relabel the right-hand subtree, and then that's going through that function. And then we're getting a new fresh label out at the end here. And then finally, we're returning this as the fresh label that somebody else could use at the end. So this is quite a lot of plumbing code. I mean, if I track through this in yellow, it's coming in here, it's going down here, it's going through this function, going through this function, and then finally it's coming out at the end. And it's very easy to make mistakes with this kind of thing. I mean, when I do this with a class normally, what I do is actually play a little trick. I would typically define this incorrectly. What I would often do is down here, I would pass in the wrong label on purpose. So I would, for example, replace that by, get the right color here, replace this by N, and this would actually not generate fresh labels because I'm sending the same label down the left subtree and the right subtree. So it's very easy to make mistakes with all of this plumbing code. So I don't really want to write programs like this. You can write programs like this in Haskell. People used to write these kind of things all the time. But actually, these days, you can write this kind of program much more cleanly by exploiting monads. So before we get going with this, let me actually just fix the program again. Let me put a prime on that last variable N there so it's correct again. So the observation now, which is going to let us redefine this program using the state monad, is a very simple one. If we look at this part here in yellow, this is really a state transformer. What we're doing is taking an input state, which is the next fresh integer, and then we're giving back a result value, which is the tree of integers, and then we're giving back an output state, which is also the next fresh integer. So this is the key observation, which is going to let us rewrite this by exploiting the state monad. So now we have an instantiation of the state data type. The state is going to be an integer. So it's no longer just a completely random or abstract type. We can say the type state is now integer. So let's move on now to actually completing the definition for this in monadic style. And I'm going to start by defining a little helper function called fresh. And what fresh is going to do is give me back, in a monadic style, fresh labels. So it's going to be a state transformer whose result is an integer. And that integer is going to be the next fresh label. So how do I actually define fresh, the helper function, as a helper state transformer? Well, it's a state transformer, so I need the dummy constructor S, and then it's going to take the current state as an input, and the state now is an integer. That's the next fresh integer. And then what we're going to give back is a pair comprising the result value, which in this case is going to be that next fresh integer. And then we need to update the state by adding 1 to it, so that if somebody is going to request another fresh integer later on, they don't get the same one, they're going to get back a different one. So again, just to emphasize the point, this is a state transformer inside the brackets here. This is the input state, n. Then we have the result value, which is just a copy of the current fresh variable or the current fresh name. And then we have the output state, which is n plus 1. And the type for this is very interesting. And again, you can think about this kind of under the water stuff. Fresh is basically giving us back an integer. That's the stuff that's above the waterline. That's the stuff that we care about. We just want to get a fresh integer. But in a pure language such as Haskell, we need to have some kind of state under the hood or under the water, and that's what the state transformer machinery is taking care of for us. Okay, so let's move on now and complete the definition of our monadic labeling function. So we're going to define a function called mlabel, give it a different name now because it's a monadic labeling function, and it's going to take a tree of A as input. That's the tree that we want to label. And now we don't need to worry about this kind of threading of the state, the integer, into and out of things like we did with the rlabel function. We'll just use the st machinery. So we're going to have st of tree of int. And again, this is going to kind of handle all the threading of the state for us automatically. So how do we actually define this in practice? So we'll do it by skeleton form as usual. So we're going to have a leaf, which has got a value x, and then we're going to have a node with a left subtree and a right subtree, and we're going to do something with that. And notice here, so let me make a little bit more space, we're not having to pass in a number n. When we did the rlabel function, we passed in this additional parameter n, which we had to thread all around the place, and we ended up with quite spaghetti-looking code. But now the n is kind of encapsulated or hidden below the waterline by the state transformer machinery. So st is a monad, so we can use the do notation. So we'll exploit the do notation here. All we're going to do in the base case is we're going to grab ourselves a fresh label. So we'll say n comes from fresh, and then we're going to build or return leaf of n. Okay, so this is a very simple two-line definition for the base case. We're simply going to get a fresh label, call it n, we're going to put that into the leaf and then return it. Okay, so a nice simple two-line definition. What happens in the recursive case? Well, this is also very simple. We're just going to have a do, and all we're going to do is we're going to recursively relabel the left subtree. So I'll call mlabel on the left subtree, and that will give me a labeled tree L prime. I'm going to call mlabel on the right subtree. So I will recursively relabel the right subtree, and I will call the relabeled tree R prime. And then all I need to do is I need to package that up as a node, L prime and R prime. And I'm done. Okay, and I think this is a much cleaner and much nicer program than the kind of manual one that we just wrote, which had all this spaghetti plumbing of labels all over the place. In particular, there's no plumbing of labels anymore because that's all handled for us behind the scenes with the ST machinery. Above the waterline, we just program in the way that we would normally like to think, kind of operationally in this case. So all we're doing in the base case is we grab a fresh label and we form it into a leaf and return it. In the recursive case, all we're doing is recursively relabeling the left subtree, recursively relabeling the right subtree, packaging those things up into a node and returning them. And again, all the plumbing of the labels and making sure that everything goes through in the right way, that's handled automatically for us by the state transformer machinery. So no plumbing code anymore. And notice that this starts to look quite like kind of old-fashioned imperative or procedural code, but it's not. It's pure functional code. So we've got a pure function that takes a tree as an input and is giving a tree of integers as an output, but kind of behind the scenes, we're exploiting the power of the state transformer monad to actually kind of thread the labels through for us automatically. So just to wrap things up, you might be thinking, well, that's not the actual function that I want. I actually don't want any state involved in the end. I just want to relabel a tree. So we could wrap this up. We could define a top-level labeling function. And this thing is going to take a tree of A's. And it's not going to have any state involved within its type at all. It's going to give back a tree of integers. So this is the basic top-level function which we want to write. So how do we write this now? So we label a tree, T. So there's a few bits and pieces. So let me just write down the definition, and then I'll explain what is going on. T, and then 0. Okay, so there's the definition. What's going on? So we're taking a tree T as an input, and that's a tree of A's. And we want to relabel it so that every leaf has a fresh integer. So what we're going to do is we're going to apply our monadic labeling function to that tree, and we're going to give it as an input the state 0. So that's going to be the first fresh label. Okay, so we're just applying the monadic labeling thing to the initial state 0. Then that's going to give us back a pair. It's going to give us back a pair of the labeled tree and the next fresh label, but we don't care about the next fresh label at this point. All we care about is the tree, so we'll do FST, and that will give us back the tree. And that's basically saying we can ignore the final label. So that's the top-level function. Again, that's just a pure Haskell function. It takes a tree of things and gives back a tree of things, but it's defined, interestingly, in terms of this function here, which is kind of hiding all of the plumbing of the fresh label for us. So at this point, you really start to see the power of the state monad and how you can use it to kind of streamline and write very clear and concise programs that manipulate state. So that's it for today. We will have our final wrap-up lecture on monads next time around.